Give me a second. Yeah, before I introduce the speaker and the topic to you, it's my duty to read out the rules of this webinar. First, registered participants for CPD points have to appear live on webcam. However, for the ladies, there is an exception. If they wish, they can cover their face while appearing live on webcam. Second, during the lecture, microphone of all the participants except that of speaker shall remain in mute positions. At the end of the presentation, there will be a 20 minutes question answer session. The facility for asking the question is only through typing in the chat box. Facility for asking the questions through microphone at the moment has been suspended. Now about the speaker. Today's speaker is Engineer Rizwan Mirza. His very brief introduction. Rizwan Mirza is already well known to many of you. He is a consulting civil engineer possessing 43 years of rich and versatile professional experience. His special interests include structural engineering, earthquake-resistant design for scenic engineering, technical specification writing, and construction contract law. Mr. Mirza has designed structures in reinforced and pre-stressed concrete, structural steel, timber, and brick masonry. In addition, he has been teaching, serving on industry, academia, liaison committees of leading universities, lecturing and writing. He is a founder member of Pakistan Society of Civil Engineers and a chief editor of its publications. Today, I am really honored to present Engineer Rizwan Mirza to you, and his topic is Design of Concrete Slabs and Introduction. Rizwan, the floor is yours. Please go ahead.
Thank you, Tahir. Let me share my screen. Yes. Give me a minute. Okay. I'll begin with a brief overrun of the history, which is relevant to today's topic. And instead of reading the slide, I'll just say that the present name of concrete is traced back to Latin word concretus, which means grown together or compounded. Romans made extensive use of concrete in their buildings. Most well known of these are Colosseum, this is CE 82, and Pantheon, completed in around CE 128. They contain large amount of concrete. But as we will see, the concrete as we know it today was quite different from concrete that can be traced back to more than 6,000 years ago. The Egyptians also made use of materials which were akin to concrete, but again, not the concrete as we know it today. The Great Wall of China also has materials which are akin to concrete, but not the concrete as we know it today. This is the Pantheon of Rome. This is the Colosseum of Rome. And this is a Saxon concrete mixer. Saxons were the tribes in the Great Britain. This is CE 700. This is where the modern concrete began. This is CE 1824, and this is a milestone in the history of concrete when Joseph Aspidine invented the Portland cement. The Portland cement was the material that changed history because it made possible the introduction of reinforcement within concrete, which provides an alkaline environment that prevents the introduction of the onset of corrosion. So it was such a big achievement that people were quick to patent the material, and the first thing that was made were pots used in gardening and a boat. Later on, this boat, which is a very small rowboat, took the shape of very large ships, which were made in concrete. And this ship that you see at the image below is traced back to 1919, which is the period of World War. Another milestone was the reinforced concrete bridge that you see in the left picture. That is 1889, is 29 feet long. At the right is the building, which was important because it contained RCC slabs, and the corner has 200-ton weight, which is in the nature of a cantilever. So this is when we see and notice the introduction of modern concrete. This building, CE 1903, is a 16-storied reinforced concrete building, naturally including slabs. And this was considered an engineering feat at that time. Now I come to the topic itself, which is slabs, and without going into much detail, I think the diagram should suffice, as most of you are familiar with beam slab arrangement, a flat plate that has no beams and no column capitals and no drop panels. Bottom left is flat slab. American Concrete Institute distinguishes between plates and slabs. When the bottom is plain and has no column capital, no drop panel, and no beams, it's a plate, otherwise it's a flat slab. At the bottom right is waffle slab, which has openings within the concrete, and this is used when the reduction in weight of concrete or the reduction in dead load is required. More on it later. This is a plan of a reinforced concrete waffle slab. The top plan shows that the area around columns has been thickened. No material has been taken out at these locations because these locations are prone to two-way punching or two-way shear, which is the most critical problem associated with beamless slabs. So this is a typical arrangement of a waffle slab with waffles at the bottom, and there may be solid lines running along the grid line, and there may not be solid line running along the grid lines. This depends upon the choice of the designer. This is a figure that shows the formwork which is used for waffle slabs, and as may be seen, waffle slabs provide for larger depths. Otherwise, for large spans of the order, say 50 feet or 60 feet, cannot be handled with solid slabs without beams or with beams, because the self load of the structure would be much larger than the load that the slab will be called upon to support. So the trick would be to reduce the load through the introduction of empty spaces. And these empty spaces are a double-edged sword because while you save on concrete, you lose on formwork. Because the cost of the formwork would outweigh the advantage gained through reduction in concrete. So as a necessary corollary, larger spans are economically handled when the formwork is repetitive. It can be used at more than one location. Otherwise, even at one location, if one has to handle a large span in concrete, this can be used. This is an introduction to how the slabs behave. They behave elastically. There are negative and positive, that is, moments causing tension at the top, tension at the bottom. Within the spans, there is tension at the bottom, and at the top of the supports, there is tension at the top. While if you continue to load the slab beyond elastic range before the yielding starts in reinforcing steel, the plastic hinges would be introduced. And as the plastic hinges form at moments of, at locations of high moment, the moment may be redistributed provided there is enough capacity at the span locations, which means that if the spans have been designed for larger moments than required by elastic analysis, there will be capacity in these spans to receive the moment shed by the supports through the formation of hinges, and the total moment remaining the same, the moments will be redistributed from the supports towards the span, provided there is a capacity within the spans. If you load the slab beyond this range, the moment action may exhaust its capacity, and the reinforcing bars acting alone would make the supporting system for what originally was a slab. The support would now be in the nature of a catenary, in the nature of a hanging cable, and provided the reinforcement has been properly anchored at the supports, the slab would not collapse. So it's a very resilient element, as one would like to state, and making a slab collapse very easily is a difficult task, provided it has been properly designed and properly detailed. This is just an opportunity to recall the various types of slabs that one may encounter during the practice, and the diagrams speak for themselves, except that the second diagram at the left here, this is a skew slab. It enjoys a special position. This is encountered primarily in bridges, and the bending moments are increased because of the introduction of a skew. Otherwise, these slabs can be handled by one or more of the techniques. More on it later. The loads can be uniformly distributed. They can be linear. They can be line loads, as we see here, as are introduced by the presence of partitions, and they can be concentrated, as we see here. A column sitting at somewhere within the span itself with no support underneath. This is a concentrated load, and there may be loading in the nature of a moment at the end of a slab. This is the diagram recalling that the location of the loading points needs to be carefully handled, because if you load all the spans at one time, you may not be able to achieve the maximum positive moments or maximum negative moments as they are required. The first diagram that you see is the influence line diagram for the span AB. And if you load this span and then every alternate span by 75% of the live load, as the codes permit you to do, you will achieve the maximum moment at this location. So this diagram shows that load this span, this span, this span, and do not load these spans through live load. Here we have an influence line diagram for the bending moment at this location, which is the support. The loading would be introduced at the two adjoining spans and then at every alternate span. These diagrams have been prepared using Moeller-Winslow principle, which give a unit rotation at the location where you are interested in the relevant stress function, which in this case is the bending moment. So the sliding is not permitted, so shear is not allowed to perform work, while the rotation only is performed, and this angle between these two lines, tangential lines, is unity. You can read about it in any of the standard texts on structural analysis. When you approach the design of a slab, you handle strength and you handle serviceability. Serviceability caters for deflections, it caters for cracking, and it caters for vibration. So you must not be oblivious of the duty to handle serviceability. Providing reinforcement may not be the sufficient step for ensuring that the slab doesn't fail. Failure does not mean collapse. When a slab or any element for that matter fails to perform the intended function, intended purpose, it is said to have failed. So failure would be characterized by the failure of the element to perform its designated duty. Now for analysis and design. I'm proceeding rather quickly, I'm aware, but I wish to cover as many aspects as I can so that you can read about these aspects later and fall back on what we talk about here, so that you don't miss out anything. Slab is a very complex subject. As you would notice that my chapter or my section is a hybrid section, which is labeled as analysis and design. This is a unique or singular example in reinforced concrete, where the concrete codes of practice provide you guidelines which are unified guidelines for analysis and design, because slabs are not very easy to analyze. They are very complex elements. So the designer, which is working in a design office, needs to be provided mechanisms for analysis as well as for design. So to keep things simple, I would tend to classify your analysis into two parts: elastic analysis and plastic analysis. Finite element has been mentioned here. It's just a numerical technique which handles cases where the loading is very unusual in its disposition, and where the edges may be very unusual in their geometry, and where the geometry in general is crooked. So one can very easily handle situations using finite element technique, choosing the appropriate finite element type, geometry and the size of the finite element itself. Elastic analysis is the theory of elasticity-based analysis, which provides a means for finding out the moments and the displacements at various locations. The plastic analysis essentially involves stages where hinge formation has been introduced, and the plastic analysis techniques are divided into two parts. Or they have classically been divided into two parts. One group is upper bound theorem, which is kinematic principle, which ensures that we have identified a mechanism whereby there would be a failure of the system, in this case, the slab. And once you do that, we can say that if there is no other mechanism, the slab or the element would undergo failure, at least under this mechanism. So you cannot be sure that the loading that you have determined is the actual loading that can be withstood by the system, but you can say that it is the upper bound on the loading which can be withstood by the system. The actual loading that is permitted may be this loading or a lower loading. On the other hand, there is another competing method, again, plastic method, which is based on the lower bound theorem. Lower bound theorem is a static principle whereby you identify a static diagram and you say that this is the load path that I have chosen for the element, in this case the slab, and the load that I have determined is certain to provide a load path for the element, and the actual load that the system can withstand would be either this load or a higher load. So this provides you with more certainty, and this is a conservative procedure. This is the elastic analysis result documented by many texts. Modern texts also cover this procedure, and you will get the equations and you will get the relevant constants. In this case, beta double prime is the coefficient, and I have a table attached on a subsequent page, which provides you a means for determining the bending moments, in this case, a simply supported rectangular panel. These are the coefficients. Mx is the bending moment in the shorter direction, which means stretching the fibers along the x-axis, and My is the moment in the longer direction, which means stretching the fibers along the y-axis. I think a short remark at this point in time would be most relevant, that the definition of the moment, the designation of the moment by classical mathematical technique is providing a subscript of the axis around which the rotation of the curls of your finger define the direction of the moment. By that concept, you point your thumb along y-axis, and the curl of your finger would provide the positive direction of the moment, which is different from what most of the software that you find in the market today. They would designate a moment which is stretching the fibers along x-axis as moment xx, and the moment that is stretching the fibers along y as moment yy. So there may be a pitfall for some who are not very careful. Now, an important thing which I wish to highlight is that the previous versions of ACI code dating back to 60s provided coefficients for the analysis of the slab, rectangular slab panels. And what I need to emphasize here is that those moments were lower than the moments provided by elastic analysis. This is WL squared by 20, while this is WL squared by 27. This is WL squared by 18. This is WL squared by 22. This is WL squared by 9.83. This is WL squared by 11.35. So there's a reduction in the X direction moment of 75.75, 0.79, that is 25%, and it gradually, the difference is lowered. And again, here, there is a clear trend that the code-based moments are lower than the moments which are determined according to the elastic theory. The contribution that I can make today is that there is a reason why these moments have been kept at a lower value, because you have been provided guidelines for designing the slab as a whole, and you will provide reinforcement for a large area, if not for the entire slab, a large width based on the same moment, and recognizing that there is a transverse redistribution of the moments. The adjoining strips would be sharing the moments of strips, which is first appearing on the central strips, which are subjected to the peak moments. So the transverse redistribution has been recognized and has been used to cut down the peaks to lower levels. This is one reason. Second, there was testing at that time in various universities which determined that the actual load withstood by the slabs, reinforced concrete slabs, is higher than that predicted by the elastic analysis. And third, the yield line theory had appeared by that time, and use was made of the modified yield line theory to change the options that were provided within the slab. Hence, to summarize, one should expect that the code-based elastic moments, as they appear in older textbooks and in older version of the codes, are lower than those that we can notice in the classical textbooks of theory of plasticity. Now, I have a very limited time, so there will be location where I will just be identifying the principle and will not wait on each slide for the duration that I have waited on the previous slides. This is a triangular slab, and I just wish to say that take an inscribed circle and design this slab as an inscribed circle and provide that reinforcement for this triangular slab. This is a polygon, and if this has a number of sides, which is 5 or more, again design this as a circle. Inscribed circle has a diameter h. Use that diameter and design the slab. This is when you come to a circle, and this is how you design a circle. Circular slab as having a circular plan. Freely supported slab would provide you radial moment equal to WH square over 19.39, while at the same location, the tangential moment would have the same value. While if the edges are clamped, M or positive maximum would be WH square over 49 at midpoint, and WR negative, which is at the edges, at the clamped edges, is WH square over 32. The tangential moment would be H square over 49, the same as the radial moment, while the tangential moment at the causing tension at the top near the support, that is at the clamped edge, would be WH square over 106. This is a concentrated load sitting over a circular slab, and this can again be handled by the use of coefficients which are available. This is called C. This is a Greek letter. This just is a ratio of the location at which you are determining the bending moment. This location divided by the radius. Now, a very important and common issue related to slabs is handling the line loads. The partition loads through European guidelines probably handle very low weight partitions. If the Q is equal to about 68 pound per foot, is less than 68 pound per foot, our Q is between 137 and 68.5 pound per foot run, and for cases where Q is less than 205 but greater than 137. These are very lightly loaded partitions. So you end up, according to these guidelines, with loads equal to 10.44 pound per square foot, 16 pound per square foot, and 25 pounds per square foot. By the way, these guidelines are not very different from what you will encounter under the British standard, which is more general, where you are not restricted by the loading that have been provided. This just says that if you know the loading per linear foot of your partition, loading per linear foot of run is known in pound per foot, divide it by 10 and you get the load in pound per square. You should not use a value lower than this. If by inspection, on the other hand, you find that the loads are very concentrated and this application of this broad formula would not work, you can use a higher load. Remember that codes always provide the lower bounds of what you can do. They don't force your hand to adopting those low values. Let me give you an example. The 9 inches of masonry sitting over randomly sitting over your slabs may lead to a loading of say around 100 pound per square foot, additional loading. 4.5 inches wide or thick brick masonry randomly placed over your slabs may lead to live load, a loading of about 60 pound per square foot. Now the two methods which are Hillerberg's method, which is the strip method, which is the method based on second theory, which is the lower bound theory. The most common method is Hillerberg's method. I have developed guidelines for you. Again, this is very arbitrary. You can handle it either by dividing the slab like this, dividing the slab like this, or dividing the slab like this. In the first part, you say that 50% of the load is taken in the x direction, 50% of the load is taken in the y direction. So W by 2 in the x direction, W by 2 in the y direction. and you get W by 2 into X square by 8, which is WX square by 16 is the bending moment in the X direction, while the W moment is in the Y direction is again WX square by 16. The distribution between X and Y direction can be made assuming that the loading in each direction, the fraction of the loading in each direction would be length of the opposite direction raised to the fourth power divided by length of that direction raised to the power 4 plus length of the orthogonal direction raised to the power 4. So that can be used as your guess. It remains a guess. This is not an elastic analysis. This again is another method by which you divide the slab into edge strips and the middle central strip of L by 2 and edge strip of L by 4. And here you assume that 50% of the load is going in this direction, 50% of the load is going in this direction, assuming that the slab is square. And here you assume in this edge that 100% of the load, which is W by 2, is moving in this direction. Nothing is moving in this direction. Here you assume that W by 2 is moving transmitted in this direction, and W by 2 is being transmitted in this direction. If you cut a strip here, you note that W by 2, which is the loading here, assigned to this direction, is being transmitted along x-axis in central L by 2 region, and full loading, that is W, is being transmitted in the edges, at the edges in L by 4 length, and you get a bending moment constructed by simple analysis. So the moment would be WL 5WL square over 64. If you run a strip from here, you will notice that there is no load being transmitted in the X direction. This is vacant, while 50% of the load is being transmitted in this direction. And the bending moment diagram would show that the peak bending moment is WL square over 64. This is 5 times as much as this value. So you can provide different reinforcement here and different reinforcement here. This is what other theories also suggest, that the edges are subjected when they are supported edges. That is, when you are separately designing the beams, not coupling the design of the beams along with the slab, would be subjected to very low forces. According to some codes, if the edges are very rigid, say like walls, or if you are separately designing the beams, these areas can be designed using minimum reinforcement, temperature and shrinkage reinforcement. This is a third method. I will not waste a lot of time here. Let me move to yield line theory, which is another plastic analysis technique. Yielding starts in the slab in this direction. It proceeds towards the corners, and a mechanism is formed when the yield lines have reached the corner. These are the various types of configurations of yield line that we see in various types of slabs. And you can find out the forces carried by these slabs, the loads carried by these slabs, by using yield line analysis. I've used a simple slab, simple one-way slab fixed at the end, assuming that the top moment capacity at the left is 6 kip-foot per foot. The top moment capacity at the right support is 10 kip-foot per foot, while that at the near the bottom, near the center, at the bottom, near the center is 4 kip-foot per foot. Knowing the properties, which means that the slab is not isotropic, and this is not having the same property at all locations, reinforcement arrangement is different. The question is, what is the load that this slab can carry? I do not know where this yield line will be formed. I assume that this is formed at a location X. At a location X, you set up the hinge, And the principle is that you equate the external work done to the internal work done. External work done is loading divided by the projected displacement of the entire area multiplied by the centroidal movement. And when you do that, you get the work done by left part and the work done by the right part. And this can be very easily computed using these equations. That is W into delta C, it's sigma of this. Delta C is the deflection at the centroid of that segment. So the UDL would undergo a movement which can be computed if you know the movement here. If you say that this is delta, you can go to this location where the centroid is located. In this case, it is half of this, and you multiply the load with the movement that is the centroidal movement, and that will be the work done. Similarly, the rotation multiplied by the moment, plastic moment at the center will be the internal work done. When you equate the internal work done with the external work done, this is the internal work done. This is a very simple equation. The angle here is θ1, this is θ2, and that can be determined by delta. Delta by x is tan of this. If it is in radian, it is directly theta, and delta divided by 12 feet is the span of the slab. 12 minus x is the angle on the right direction. So this is the work done. If you use the basic principle that work done, internal work done is equal to external work done, this is the equation that you get. While the answer that you need is the location of x. You use different values of x and you provide WU that you can treat as the safe load for the slab, and you find that it is somewhere in between. So you say that 0.662 KSF is the load that this slab can be subjected to, and the location of the hinge would be at 5.5 feet. So this is a quick demonstration. This is a standard solution for a rectangular slab. You can look it up in any textbook. This is a standard solution for this triangular slab with two edges, not necessarily equal, and fixed edges and free edge, completely free, no support at all. The equation has been given, you can determine the load. Go on. Now let me move on to the ACI method. ACI provides two methods which are essentially the same, except that in one approach you undertake a longitudinal analysis as one would be expected to in all cases, and in the second approach, code provides you with simple guidelines, and you do not have to perform a longitudinal analysis. And code says that you can provide the code specified method or any other method which satisfy the strength criterion and which satisfy the serviceability criterion. So don't say that if somebody adopts a different criterion, the criterion is non-compliant with the ACI requirements. But you have to demonstrate that the serviceability and the safety have been ensured within the meanings of the code. Equivalent frame divides the slab into two directions. Each direction is a beam slab to the center line of the next transverse span. This is the direction of analysis. This direction. This is direction 1. This is direction 2. to the center of the next span, you cut off the entire thing, and to the center of the next span, to the left, you cut off the entire thing, and this becomes the beam slab. This is direction 1, this is direction 2, this is the column, and this is the beam slab. Be they be with beams or without beams, ACI provides only a unified treatment of beam slabs. And it's very important for you to understand that when you say that there is a beam underneath the slab, if the beam is projecting only 1 millimeter below the slab, would you by common sense designate it as a beam? Probably not. If it is projecting 1 meter below the slab, would you designate this as a very rigid beam? Most probably for many values of span, you would say that this is a fairly rigid beam. So the very word beam doesn't mean that there'll be a shear, a very large shear resisted by the beam. Basically, the loading is distributed between what is known as the column strip and what is known as 2 middle strips. This is the column strip. This is a rigid part because it is in the line of the columns. The remaining part is this middle strip. If you have a beam here, the beam would take a lot of moment in this region, and the slab surrounding the beam would have to shed that moment and apportion it to the beam. This is it. So we cannot say that first I will design the slabs and then I will apportion that load to the beam, and then I will design the beam for that loading. This is the ratio of the stiffness alpha sub F, beam and slab, which is E sub B, concrete modulus of elasticity of concrete, into I sub B, the moment of inertia of beam, divided by E sub B divided by I sub S. So when you use a slab width, this is from here to here. And when you use slab width, which is from here to here, not the entire width. Okay, now this is what you do. The moment is transmitted to middle strip, and it is transmitted to column strip. The column strip moment is transmitted to beam, part of it, and part of the moment is transmitted to slab. Part of that part of moment which is transmitted to column strip slab is again divided into a width, which is the transfer width, which is the width of the column transfers to the direction of analysis, that is C2, plus a slab width equal to 1.5 times the thickness of the slab on each side. More on this later. And the remaining part of the slab is normally designed as you would give a shear, which is the same shear as is determined by determining the shear of the column strip. This is just to check that this area has adequate reinforcement or not. A direct design method, which gives you the freedom of not making a longitudinal analysis of the beam slab system, says that there should be at least 3 spans, the slab should be rectangular panels, the length to width ratio should be at least 2, the shorter span shall not differ from the longer span by 1/3 the dimension of the longer span. Column offsets in each direction shall not be more than 10%. And it can handle only uniform loading. And live load should be less than or equal to dead load. That's it. No redistribution of moments is permitted. So again, this is the same division. Remember that whether you are analyzing in the X direction or in the Y direction, the column strip width is always determined by the shorter direction at each location. If you are sitting here and you are designing in this direction, you just look at the two directions, and the shorter of the two spans would be the governing span, and you will use half of that span as for computing the width. And the remaining part or the residue would be designated as the middle step. Now, the direct design method, which is the easier, which is a concession, which is introduced by way of a concession, a simplified method, says that you just take the full width of the slab, multiply it with the load, and compute the total static moment, which is WL square by 8. Then code tells you of how to distribute this total static moment to various supports. For an interior span, 65% to the support, 35% to the span. Similarly, for other locations, the code provides guidelines, and these are the tables. For the interior negative factored moment, L2 or L1 must be determined. So for the ratio 1, it is 75%. For the exterior negative factored moment, when beta T, the torsional ratio between the slab and the beam is 0, 100% shall go to the column strip. And positive factored moment in the column strip is 60%, when alpha F1 into L2 over L1 is 0. So it's very sensitive to the aspect ratio of the slab panel. L1 is the direction of analysis, and L2 is the direction perpendicular to the direction of analysis. I'm sorry, I'm moving a bit fast. I am apologizing again and again. I have very limited time at my disposal. I have to leave 15 minutes clear at the end for questions. So this is just a summary of how the table behaves. When L1 over L2 increases, width of column strip increases as a function of the total width. And this is what you must note. So its shear increases. Column strip shear increases as L1 over L2 increases. That is, length in the direction of analysis divided by length perpendicular to that direction is increasing. So the shear of the column strip increases. Alpha F1 increases, which means that beam is very stiff. So as the beam is part of the column strip, the shear of the column strip increases. When the beta T decreases, which means that the slab is free to rotate at the end, the torsion is not there. So the share of the column strip again increases. Otherwise, the moment is taken to the middle strips through the use of the strip beam at which is the spandrel beam, called the spandrel beam. This is another issue, which is transfer within the width, of which we have already talked about. That is C2, that is transfers to the direction of analysis, what, plus 1.5 times H in this direction, 1.5 times H here. So this is the width of the slab within which every moment that is to be transferred between column and beam slab has to be made. What is this moment? At the end span, the entire moment is to be transferred. In the within this in the interior spans, if these adjoining spans are equal, theoretically the moment should balance each other under gravity loading. But if the live load is present on one side and it is not present on the other, there will be a differential loading. So the bending moment um, uh, of the two adjoining spans at the support would not be equal, and the difference of the two moments would, of course, be resisted by the column. Similarly, in the case of lateral loading, the entire moment will be transferred from beam slabs to the columns, and this is the width in all cases that is required to transmit the loading from beam slab to the column. The moments applied here cannot be transmitted here. There is no column in front of these strips. So the code gives you a very narrow band from which you can make this transfer. Now, what does this transfer involve? The transfer involves two actions, flexure and shear. The flexure reinforcement can be provided within that reinforcement, and shear reinforcement will increase the shear around columns. The two-way shear will be increased. How much shear is to be registered through flexure? This is the equation that provides you with the code provided formula. Flexural shear is 1 divided by 1 plus 2 by 3 of B1 over B2 under root. B1 is the direction of analysis dimension, and B2 is the orthogonal dimension. For a square column, this becomes 60%. So when this becomes 0.6, this becomes 0.4. The sum remains the same. This graph shows that the blue line is the flexural shear of the moment to be transferred. Red line is the shear. When the 60% load is being transferred through flexure, 40% load is being transferred at this aspect ratio. So on, you can read this graph or you can directly use this equation. So this is what shear transfer looks like. The moment transfer moment is acting here, and this is the direct shear, and this is the torsional shear. And when you combine this direct shear with the torsional shear, this is what you get. The shear is increased here and it is decreased here. And similarly for the H1. And these are the coefficients which are used for determining the value of the stress. And these coefficients J and C are provided within the code. You can use them here. I do not have enough time to cover it here. Reinforcement, as you know, is guideline is provided within the code. 0.002 of the gross area of the slab is the minimum for grade 60. Grade 40 or 50 reinforcing steel. 0.0018 is the minimum area for grade 60. And remember that unlike the case of beams, it's the H which is used for determining the concrete area. That is width of the slab, that is unit width, multiplied by the total thickness of the slab, not D. When you determine the minimum reinforcement of beams, D or the effective depth is used. Okay. Maximum bar spacing at critical locations is 2H for a mat, for loaded slab on grade. Other than critical sections of one-way or two-way slabs, it is 3H, less than or equal to 18 inches. And where at locations where there is no bending, 5H. The values, the numbers were very different when I had started my practice back in 80s, but they have been modified greatly with time. And if anything, the spacing has been reduced. because of the fact that large amount of cracking has been noticed in the slabs. Anchorage is a very important issue. I will approach it very simply that if you increase the diameter of the bar, the area of the bar would increase by the square of the diameter, while the perimeter of the bar would be increased linearly. So as you increase the diameter, the perimeter will not be able to keep pace with the increase in the square, with the increase in the area. Area reflects the force that will be generated, while the perimeter reflects the surface available for transmitting that force to the surrounding concrete. So ratio between perimeter and area becomes very disadvantageous as you move towards larger diameters, and they are very difficult to anchor. At certain diameters, the code doesn't even provide a freedom for lap splices. This is how you terminate your bars. You can look it up in the code. There is nothing for me to repeat here. This is just to tell you that the column strip and strip are treated differently, and that's it. A shear has two parts, two-way shear and wide beam shear, but I must say that shear is shear. Whether it is acting around a column or it is acting along a line, a shear is a shear, and it has disastrous effects. It is a non-ductile failure. It is sudden, and there is no redistribution. The two-way shear, the one-way shear has this nature of crack, and 2F sub C prime under root is the allowable value for the permitted stress, and two-way shear has a formula for allowable stress, which at best can yield 4F sub C prime under root of the allowable stress, but the formula reflects the aspect ratio of the column, 2 plus 4 over B, and when this is 2, 4 divided by 2 will become 2, and 2 plus 2 will become 4. When the aspect ratio becomes long, or the column has a look in the nature of a wall, this advantage of two-way, higher two-way shear, allowable shear is gradually lost till such time that you practically end up with 2F sub C prime. You can read about it in a textbook. The perimeter should be the minimum that is possible for the shape in question, but need not approach closer than D by 2 to the element involved. This is the typical example of how you would handle the stand design. 5E sub C plus 5E sub S should be greater than or equal to B sub U. But remember that whenever you are using reinforcement, the advantage of using 4F sub C prime under root or a higher value higher than 2F sub C prime under root has to be surrendered. It will be reverted back to 2F sub C prime under root, and you will compute your calculation. This is how your reinforcement is placed in the punching shear. This is what the reinforcement looks like. Handling the openings has two parts. You will have a effect on shear, and the code says that just if the opening is within a distance of 10/8 from the center of the element, just join the edges with a straight line and do not include this perimeter within the capacity. This is a simple guide. You lose on the perimeter. Here there are two openings, so you join it like this, you join it like this, and this width is gone, this width is gone. So you use this width, and this width, and so on. This is for flexion. There are three areas for the middle strip zone. The green zone, as I've shown it, you have no limit on what you can do. And for the amber color, you can cut off. You can interrupt 1/4 of column strip or middle strip only. And in the red area, you can cut off only 1/8 of column strip. But if you take my advice, of course, as an individual, the code is the final authority. I would tend not to have any opening in this region. It's a very dangerous thing to do because the entire movement is concentrated in a column strip. Once you have done it, once you have decided on the permissible width of the opening, you have to provide the capacity, eke out the capacity shortfall through introducing additional reinforcement. That has to be done in any case, which does not mean that you provide this opening and then forget about the loss of flexural capacity. You have to eke out the capacity shortfall through providing additional reinforcement around the opening. Deflections are handled by a method which is called a deemed to satisfy method. You use the code specified procedure for one-way slabs, L by 20, L by 24, L by 20, L by 10 for cantilever, and this is percentage. This is the H. But don't say that I've used this and still my slab has deflected. This is for usual loading. If your case is unusual, be careful. Two-way slabs. Well, this is the formula. When the alpha m is not very large, use this formula. When the alpha m is greater than 2, use this simple formula. This is 39 when beta is 1, 39 plus 45. This becomes 45. This becomes 1.1 when 60,000 reinforcement is used. So it is a longer span into 1.1 divided by around 45. You know, read the entire formula if you want, but I'm just trying to. I do the complete number. 36 plus 9 into long side divided by short side. Store it in a calculator, and then long span into 12 into 1.1 divided by the stored value. For two-way slabs, this is the type of answer that you get. And alpha is less than this. The code provides you with guidelines. It doesn't provide you with the formula. It says that this is the actual number by which you will divide your span when the alpha m is very low. You are moving towards flat slabs, as you would call them. This is the summary of the code provisions. Now you can also adopt not to use deemed to satisfy criteria. You can compute your number, compute the deflection by one of the techniques. But this is where I have computed the delta maximum for a uniform load over the entire plate. For a rectangular plate, the answer is WA4 over 22 EHQ. You can use it, use a multiplier to account for long-term deformations, and then say whether you accept this deformation or you don't. This is the number that may be used for non-square plates. This is the multiplier for long-term deformations. In a span of say 5 years, the number becomes twice as large. For sustained loading, you multiply your sustained deformation, deformation under dead load becomes about double. So these are the guidelines that permitted deformations, and when you are computing the deformations, the table can be classified into two parts. One, roofs and floors. The code here is dealing only with immediate deflections. L over 80, 180, L over 360. Not attached to non-structural elements likely to be damaged by large deflection. This is one. Not attached, but this is floor. Floor not attached to non-structural elements. This is L over 360. So lower deflection is allowed here. This is roof or floor. Roof or floor. Attached to such sensitive elements, not attached to such sensitive elements. But the deflection is not measured. It is dead plus live plus creep. That is long term. So the criterion is L over 2. Read about it. I'm sure that you. Other researchers have gone for much lower values, L over 2 for 1500. And they say that unless you do it, you should be ready for cracking within your partitions. This is again a hoax, which is used by many designers, which say that I provided a camber, pre-camber in my slab, so I don't need to worry about deflections. This is not correct. Deflections would be there whether you provide a camber, pre-camber, or you don't. It's a cosmetic solution. If the slab moves by, say, 1 inch or 25 millimeters, and if you move your formwork upward before pouring of concrete, it would become horizontal upon loading, and you will not notice, but the movement has taken place. So when that movement takes place, needs to be noticed, whether it takes place after the introduction of partitions or it occurs before the introduction of partitions. Cracking needs to be handled. In the 70s, high strength steel was introduced, and which is grade 60, and strength design methods were introduced. Reinforcement was halved by strength design method, and the reinforcement was divided by about 1.5 by the use of high strength steel. So the strains were increased by about 3 times. So this resulted in the onset of cracking. Measures are use low closer bars, small size bars. Use them closely spaced. Reduce your stress. Code also provides you with the maximum maximum value. Again, but you should keep your eyes open. And there was a Gray loops equation, which was part of the earlier codes that doesn't appear in the codes today, but it gives you some idea of the amount of deflection that is to be expected. Yeah, 0.3 millimeter is the accepted deflection by the European code, EU codes 2, which is equal to about accepted deflection of 0.31 by FIP, which is again a European code. This last part, second last part of my, I'm sorry for bearing with me for this large speed words per minute talk. The dynamics of the slab is very important. The resonance can take place. Machine design may ultimately damage the slab. When you design it for placing a machine on the slab, it may ultimately damage the slab, and human perception may have psychological implications. So just to give you a background of what you have read in your schools, this is a pendulum moving in around the mean position. So the omega of this movement is K over M under root, a well-known relationship. This is the linear component. When you look at location 2, this is how it moves, and the linear part can be converted from the sinusoidal movement. This, interestingly, was noticed by Galileo. Galileo was a very amazing person. As 1564, 1642. If I correctly recall, this is the year 1642 when Isaac Newton was born. And he used to observe in the churches the movement of the large bells. And he said that I have noticed that for every bell, there is a unique period of vibration. And no matter how far from the mean position you pull and leave it, it will take the same time for coming back from one position to the other extreme and then back. He was blind then when he dictated this relationship to his son. This again is an attempt to convert or to visualize the sinusoidal movement of pendulum. This is how the disturbance is, and to a linear movement of a spring. Just to give you a qualitative figure. This is a very interesting recent example of Korea when on the 39 plus 6 storied building in Korea, Seoul was noticed to have started vibrating. It continued to vibrate for 10 to 15 minutes. And it was a great, enigma for the people, and many people were collected who would analyze the problem. And they said that this is basically resonance, one wave with the same amplitude, same frequency, adding up to another wave with the same frequency, resulting in a very large amplitude. They must have the same frequency, and they must be adding up at the right places. So the frequency was noticed to be around 2.6, the period cycles per second, omega 1. Sorry, this is hertz. This is cycles per second. I'm so sorry for this mistake. This is cycles per second. So this building started moving laterally with an immense force for a good 10 to 15 minutes when the people at the 12th floor were undergoing an aerobic exercise training. Look at what dynamics can do to a slab. It's very important that you design your slabs that do not behave in this way. This is various edge conditions of a slab. Alpha is the constant that you need, and for various values of alpha, you use plug in alpha here and compute the frequency. ET cube over 12, 1 minus nu square, counting this m out is the stiffness of the flap. This is like K over m under root. So alpha is the constant that you will get from that table, L is the span. So you can compute your frequency, and this is the damping, that the motion would not go unchecked. The initial amplitude would gradually be reduced. So you divide the damping into structural damping, damping due to furniture, and damping due to finishes. So the damping would be D1 plus D2 plus D3. And then you determine your natural frequency, your mass, which will be included, and your damping. Read off the one step root mean square value for 90% probability, and then determine acceptance class. Let me take you to the graph. This is what the graph looks like. For the relevant value of damping, enter with your frequency and the mass, and you strike E here, for instance. So this is the acceptance class E. This is where it is acceptable. This is adjustable in sports, in industry, not in health, not in residential. So change everything so that you come here in the green part. See, Sashmipur Vein is just one diagram. You can look it up in the code. except that I must remind you that in zone 2A and 2B, 2B at least, the 2A and 2B, at least 1/4 of the reinforcement at the top in the column set must run all the way. You cannot terminate it. You cannot leave this area unreinforced. There are other provisions which relate bottom reinforcement if not less than half the top reinforcement and similar provisions. These are very simple. I mean, if you get just aware of the chapter 21 requirements, I think this is it. So I must thank you and apologize once again of moving so fast. This is not my way. I would tend to speak slowly when interacting with people, especially when I'm talking to my colleagues at my office. But in this case, as my opportunity to speak comes after after a period of about 2 or 3 years, I want to utilize this time to interact fully with you, and I'm sure that you can go home and read about these things. And if you have any questions, I would be available to personally answer your question even after this session is over. And my number can be obtained from Sadia Naveed, and you feel free to call me if you have any difficulty. Thank you very much. Thank you very much for bearing with me. Thank you all. Thank you, Time.
Thank you, Rizwan, for throwing such a deep insight on the design of the slab. Now, so far, I don't have one question, but I have one comment, which has come from Ijaz Ali, and while I was, and he is saying, I think he's asking about this MX value of the code, and he's saying it is greater than that of elastic method. Did you say anything contrary to it? He's saying kindly correct the ratio. MX value of the code is greater than that of elastic method.
Okay, which code is he talking about? Ask him, which code is he talking about? I have used the direct numbers from the code and I have noted the numbers exactly, very faithfully. I feel he's using some other code or some other table. There are 3 methods in the code, method 1, method 2, method 3. Certain methods are conservative. These methods are the ones that provide you to use one allowable value of the moment coefficient for dead load and live load. That's a conservative method. The one that provides you with separate coefficient for dead and live loads are less conservative. This would depend upon which of the 3 methods he is referring to. Not saying that his comment is incorrect, but I'm just saying that my observation regarding lower values of moment coefficients in codes is a very, very well documented concept. I'm not the only one who has discovered it. It's covered by books. It's been covered by articles in the journals that the coefficients are lower, and the reasons that I have cited for the low value of the coefficients are also very well known. But still, if he has a question and if he has identified something, he's free to get my number from Sadia and communicate with me directly. I would be ready to look at what he says and see where there has been a misunderstanding. But my general conclusion is correct.
So we have another question from Adnan Dar. He's asking which method of analysis can be used for slab placed on masonry wall.
Okay, slabs placed on masonry walls. I think code-based coefficients would be best because elastic coefficients will give you higher values of moments. Because you will get a peak at the middle. The earlier participants failed to identify where he is reading the value. The value at the center is the highest value. As you move away from the center, transversely away from the center, the values fall off. So if we design, I'll come back to the second question later. If you design for the peak value of the central strip, it is certain to be very high. But if you move away from the center, values would gradually fall down. Now for the second question, I would say that the code coefficients of the earlier codes, as they appeared once and then only time, they would be best because they allow for a reduction in moments. They will be economical. Otherwise, if he wishes to use the coefficients of elastic theory, he will get a higher number for reinforcement. It will be safe, naturally safe.
Yes, thank you, Rizwan. Now there is a comment from Suhail Raza. I don't know where. Let me see if there is any more question. Then, okay, Suhail Raza has appreciated your lecture, that you have covered such a vast topic in just 100 minutes, and he's appreciating your effort, and you want to congratulate you for giving such a nice talk. So, gentlemen and ladies and gentlemen, if you have any further questions, kindly type the questions in the chat box. And I did get a question from Adnan Dar again, and he's asking how can we adopt the pattern method while designing for whole slab? Did you get the question, Rizwan?
No, I don't. Unfortunately, I don't. It's my fault, I admit.
He's saying,
better method.
How can we adopt the pattern load method while designing for whole slab?
What is that word? Batten, B-A-T-T-O-N?
P-A-T-T-E-R-N, pattern load method.
Pattern load. Oh. How we can adopt a pattern load method? Yes. You can either, first you need to know whether you are using code coefficients, modern code coefficients. If your live load is very small, you don't need to adopt pattern loading for that. Code is very explicit about it. If the load is very small, the effect of pattern load or no pattern load would not differ much from each other. One. Second, if you note that as the influence line diagram coefficients for negative moments will not greatly influence the loading method, which means that if you load all the spans, while the influence line diagram for a particular negative moment of a particular support required loading of the two adjoining spans and then every alternate span, and you have erroneously loaded other spans which should not have been loaded, the effect would be low because the coefficient of those the locations, influence line diagram coefficient at that locations would be very low in their value. So the error that will be introduced would be significant in case of positive movements. So I cannot officially tell him what to do, but silently within the confines of my office, I would tend to be a little liberal with positive moments and provide for some capacity maybe slightly higher than the computed capacity for positive moments for more than one reason. For overloading, because if negative moments capacity is exceeded, naturally the moments will fall back on the positive moment. Secondly, if there is a pattern loading, the effect of pattern loading would already automatically be incorporated because I have increased the capacity. But Strictly speaking, stricto sensu, as the court advises you, you can have 3, 4, or 5 types of loading arrangements and add them up to your loads. With the advent of modern computers, I think this is very easy. The longhand method would entail what I'm telling you. Even if I have not been able to answer your question fully, again, I will say that feel free to call me up, because I would not want to waste everybody's time when my communication is poor.
Now, so we have a comment and a question from Suhail Raza. Saying there is an increasing trend in young engineers for blindly using available software for structural design. What caution do you think should be observed in using these commercial software? One, now I have, I think, the same question from Adnan, or a similar question from Adnan Dar also. He's asking why using safe software, slab detailing usually don't show minimum structural area where there is no movement. Do we need minimum reinforcement? So this, did you get my questions both?
Yeah. I got both the questions.
Okay.
Well, I will go back to the second question first, which is the smaller of the two questions. The second question suggests that safe or no safe, there are locations, according to him, at which there is no bending moment. There is no tensile stress. And he's asking me whether he should or he should not provide reinforcement at those locations. My answer to him for a mat, I'm sure that he's using this safer mat, would be not to leave any area unreinforced, whether or not his immediate analysis shows any tension on that surface in that direction. There is a reason why I say this. Everybody recognizes, and the textbooks and the handbooks clearly state that the bending moment diagram that you receive by these methods, which appear to be very sophisticated, are very misleading. And a slight change in the parameters would completely change the picture. And tension would appear in the areas where no tension initially appeared. According to the code, code says when there is a bending moment, your minimum reinforcement shall not be less than this. So when there is no bending moment, the code doesn't force you to provide any reinforcement. This is one part of the answer. The second part of the answer is that if the slab is rather thick, it's not 5 inches or 6 inches, it must be at least 12 inches or 18 inches thick or 2 feet thick, you should not leave any surface in any direction unreinforced, because the shrinkage reinforcement cannot be avoided for such large depths. You must have reinforcement on every face, in every direction, at every location, so that you can cater for shrinkage and temperature changes and such other effects. And also, as I have already said, for the possibility of bending moment diagram changing under gravity loading, as you have incorrectly adopted the subgrade modulus, or under seismic loading when the quick reversal of the moments take place. So there is no use not providing reinforcement in thick elements. In all thick elements, reinforcement must be provided at all locations in each direction, and sometimes for machine elements, even within the surfaces. There is reinforcement not only at the top and at the bottom, but also in the central region also. For Suhail Raza's question, I would say that computer software solution must always be verified by your longhand solution. Your longhand solutions shall not be verified by your computer solution. The question for which you do not have the approximate answer before starting analyzing the problem shall not be solved by you through using a software. I repeat what I say, that unless you know the approximate answer of a problem before approaching it through a computer, you should rather not solve it at all, because you have no way of verifying whether the answer that you get is the right kind of figure or it's not the right kind of figure. For mental training, a very qualitative approximate answer must be obtained before you start using the computer. A reckless reliance on computers tantamounts to abuse of the computers. Computers should be used to facilitate your work, to perform the donkey work for you, to perform the repetitive work for you. But the key concepts should be verified by you yourself through your calculator and your pencil and paper. This is the answer. This is the advice that I can provide. I have seen blunders in my life, blunders. I can give examples of those blunders, but these involve other offices who have committed these blunders, and I don't want to name anyone, because people can, by some, even if I don't provide a name, by the broad facts, the finger can be pointed at a particular office, but blunders can be committed. I hope this answers Suhail Raza's question. Thanks for him, and thanks for thanks to him for complimenting me earlier. You switched on to the next question, so I did not get the opportunity to thank him. Thanks again, Tahir. Are you there? Tahir from Wando again. क्या हो गया 4 बजे अभी तो नहीं क्या हो म्यूट हो गया नहीं अभी आते हैं वो म्यूट हो गया लोग नजर आ रहे हैं चलो क्या है नजर नहीं आ रहा शायद नहीं अब ये क्वेश्चन आया मैं बोल दूं क्वेश्चन आया तो नहीं वो पूछो तरीका ये है मैंने
Rizwan, are you with me?
Yeah, I am there.
Acha ji. Before, I just wanted to add that regarding this use of the software, that if somebody has a repetitive structures to be designed, so at least one design should be checked with the longhand calculations as you have suggested, and then they can start using the software for the repetitive design of the similar structures. I think this should be the policy. Longhand calculations should not be totally ignored, and totally dependence of on software design is very dangerous, as you have said. Now let's see another question. I have another question now. This is from Adnan Dar. There is an increasing trend in the market not to provide top reinforcement in the masonry houses. However, can we avoid top reinforcement at the discontinuous edges? Please comment, as the slab thickness is very small. Rizwan, please.
Okay. I'm not sure if I've quite understood the question. Probably what he's saying is ask him to verify if I correctly understood. I understand. I understand. Sorry.
Should I repeat the question? There is an increasing trend in the market not to provide top reinforcement in the masonry houses. However, can we avoid top reinforcement at the discontinuous edges? Please comment, as the slab thickness is very small.
Okay, okay. Now I understand. This is what I had initially understood, but was not sure. He's talking about the introduction of reinforcement at the top, while he's taking in his design the panel as simply supported at the edge. So if he does not provide any reinforcement at the top, and he is designing the slab with a edge condition that is simply supported at the edge, there is no danger as to the safety of the panel. However, a minor cracking may take place. But, for very small panels, the modulus of rupture may not be overcome when the moments are so low, especially at the top floor. He is talking basically of the first slab, which has a loaded wall at the top, and there is a wall over which this loaded wall and the slab rest at the bottom. This is where the restraint is offered. So this restraint at worst can lead to minor cracking. I would suggest that if he wishes to economize, he can use number 2 bars just to, avoid cracking at right angles to the wall. But even if he doesn't, it's not criminal. I mean, it's not a criminal thing to do. I would suggest that he does it. This is good for the longevity of his slab. If there is cracking, there will be introduction of water and oxygen, and with time there will be onset of corrosion. This is the big hazard. So I think as a responsible engineer, we should guard the property of our clients and think of not only of the strength and serviceability, but about longevity. I think he should provide number 2 bars there, say at 6 inches, whatever.
Okay, thank you very much for first I should thank the participants for asking and participating so actively in the question answer session. Rizwan, thank you very much again for your detailed lecture on this slab design. Now we really have to conclude the session here. And before I do it, I have few announcements. Number 1, the next lecture is on 10th June 2023. The topic is practical aspects of pile foundations, design and construction. And our guest speaker would be Dr. Muhammad Irfan. I again repeat, it's 10th June 2023. The topic is practical aspects of pile foundations, design and construction. Guest speaker is Dr. Muhammad Irfan. Gentlemen, you can collect your certificates from our office from 18th May, which would be Thursday. And our address, as you already know, is 14A1 Block P, Model Town Extension, Lahore. Before coming, if you want to call, the telephone number is 0347 462 5111. 0347 462 5111. Person to contact is Mr. Ahmed Akram. So with the Rizwan, your shield and your certificate, inshallah, Sadia will deliver by a special messenger to your office. So with this, we come to the end of the session. Thank you very much. And I will see you on the 10th June 2023, which is Saturday. Thank you very much. God bless you all.
Thank you.